Hey, hello everyone. I have been studying transformers and about attention for last few days, and I I really think that the concept of attention is absolutely fascinating. So I thought I'll summarize my learnings in a video and a blog, uh, so that it can help other people who are trying to learn about attention. Okay, having said that, uh, I also ended up implementing transformer attention from scratch. The link for the repo is in the description. Please have a look. Okay, let's jump right in. This, what you see on the screen, is the standard transformer architecture, the encoder and decoder one. In this video, we'll look into only one particular part of this transformer, which is this multi-head attention layer. There, we see multi-head attention layer in transformer in three places. First is self attention in an encoder. Second, we have masked attention in decoder, and then encoder, decoder, or cross attention in decoder again. All these three are very much similar. They have very few subtle differences, which we'll talk towards the end of this video. What are the differences? Let's look at simple, plain, vanilla self attention first in this encoder. Let's talk about this layer. First of all, let's understand what goes inside this layer. This layer expects a sequence of tokens as embeddings, of course. This layer expects a sequence of tokens as embeddings as input. It also outputs stack of embeddings, a sequence of embeddings. The input and output have exactly the same dimensions. The input embeddings are supposedly more refined and much more contextually aware, which helps the transformers do its thing. One more important point which you should keep in mind is parallelism. Parallelism is exactly what makes transformers as phenomenal as they are. All the tokens, like if I have a sentence which is 50 words, I'll input all those 50 words into the transformer at once. Transformer will process all these 50 words parallelly, like whatever the sequence length we are deciding. Whenever I say sequence length, you can imagine it as sentence length or whatever the hyperparameter is we are using, like the maximum length of one sequence which we are inputting in the transformer. So when these embeddings goes in the attention layer and then they come out inside the attention layer, if we look at the big picture, there are majorly two things happening. First, what is happening is we are trying to understand how these words are related to each other, right? Then we are trying to understand. Uh, then we use a second thing. What happens is we understand this relation, and then we try to come up with much more better and contextually aware embeddings. Now, what is a big deal about contextually aware embeddings? So, basically, the meanings of the word changes with the context. For example, March. March can have two meanings, like the month or the act of marching, right? And if we the embedding or the meaning will depend on the context. For example, stick. The word stick can have three meanings actually. Stick is the physical stick, and the stick, like why is it not sticking? Why is the poster not sticking to the wall? It's glued and all. And then third is the metaphorical reason that this concept is not sticking in my mind. It's not like literally sticking. It's not the literal. It's a metaphorical meaning. Everything depends on the context. So that is why I think stick in all the three cases should have different embeddings, and if we have different embeddings, we should be good. So that is why contextual embeddings are all the rage here. Moving on, let's see where I ended up writing a blog about it, basically about attention. So you should give it a read. Okay, so we covered it. There are two things which are happening here inside the layer. Let's focus on the first thing. First thing is we are trying to understand what are the relation between the tokens, between the words in the sentence. We'll understand which word is attending to which other word in the sentence. Okay. So I would like to, for intuition, I would like to give you this example. Let's just quickly look at this image. This is from Lillian Wang's blog. She has an amazing blog. So if you look at this, imagine you cannot see what is inside yellow box. Okay, just imagine. The content of these three red boxes, the eyes, the ears, and the nose of the dogs, they provide some very serious clues as to what can be inside this yellow box. While at the same time, the contents inside these gray boxes does not help us much, right? If what I'm given are only gray boxes. For all I know, that can be a human face behind this question mark. I don't know. Like, that is what attention is in a nutshell. Two things. Uh, some parts of the input will provide context about the other parts, and not all parts will be equally helpful. That's all attention is. Let's look at how it pans out in case of NLP, natural language sentences. This is what we'll be dealing with transformers. She is eating a green apple. As soon as I as soon as I read eating, she is eating. I know a food word is about to come. So there is a very strong relationship between eating an apple. And then if you see she's eating a green apple, green and apple is also related, but the relation is not that strong. Or eating and green are not that strong. So these relationships are called attention. We see high attention here, low attention here, and this is what we want to capture basically. That's all what you want to do. Let's take one more example. The animal didn't cross the street because it was too tired. It was too tired. What was too tired? Was the street too tired? No, of course not. Animal was too tired. Very obvious for us humans, but for a computer algorithm, not so much. So this is the kind of relation which we want to capture in attention. Let's see how do we do that. There are one more examples. Check it out. How do we do that? Is let's move towards the mathematics of the things. We are machine learning engineers, shall we? So in mathematics of the things, what is happening here is the authors say that to calculate these relationships, to quantify these relationships, we introduce three vectors corresponding to every token: query vector, key vector, and value vector. Every token has its own set of three vectors, these vectors. How do we calculate these vectors is we maintain these matrices WQ, WK, and WV inside the attention layer. These three matrices are layer parameters which are learned during model training. These are like weights, simply these are weights. During model training we learn these WQ, WK, and WV, and during the inference mode, whenever the tokens are passed inside this layer, we multiply those tokens with these three matrices and get the respective queries, keys, and values. This all happens inside the attention layer. Okay. Now once we have these values, we can try to get relationships. Okay, so what is a query, what is a key, and what is a value vector? Think of it like this. Query for any word is what that token is looking for. So we're looking for patterns, right? What that word is looking for is the query. Every word will be looking for something different, right? Key is what I have. So when other tokens are looking for something, I have something. So key is my way to tell them, okay, bro, this is what I have. Value is what I will communicate finally, right? So I said there are two parts of this, two things happening inside attention. One is capturing the relationships, and third is leveraging these attention or patterns or relations to refine embeddings. V, value vector, will be used in second part. Q and K will be used in first part. Okay. So let's look at these words one by one. I'll quickly move. Yeah, this Jay Alammar, this blog is very awesome. I want you to read this blog. He has captured all this process very effectively. Okay. So let's look at what is happening. Let's look at this first word, right? So I want to understand how is this related to other words. So we have query vector, we have k vector. Query is what I'm looking for, key is what everyone has. So basically what I want to find is which other tokens have key vectors similar to this token's q vector. Simple. So if q and k are similar, what I'm looking for and what you have, very well, there is a relationship. Done. So how to capture it in machine learning? We take a dot product. We know dot product of similar vectors is higher. The higher the similarity, higher is the dot product. That's why we take a dot product between q and k. So if I'm trying to understand the relation between thinking and all other tokens, I'll take the q1, which is from thinking, and I'll try to multiply it with every key of every vector. Let's say I have 50 vectors here: q1 k1, q1 k2, q1 k3, q1 k4 till q1 k50. Okay. So length of 50 or sequence length. Once I multiply, I have a score. This score is an indicator of the relation which I showed here. This score is imagine it as a thickness of this line, right? However the strong relation is, that is what the score will tell me. Okay. Now I calculate the score for every word with every other word. So just like I did Q1 with K1, Q1 with K2, Q1 with K3, I'll do it for Q2 as well. Q2 with K1, Q2 with K2, and then Q2 with K3 until K50. I'll do till the end. So I'll end up with a matrix, sequence length by sequence length. That matrix is called attention pattern. Yeah, that is what attention pattern is. That is what attention pattern is. I think, yeah. This is how it looks. This is how it looks. The attention pattern is how it looks like. Uh, Imagine these are all the same tokens. I'll come later why these tokens are different. They are different because it's not necessary that we try to find the relationship within a sentence. We can try to find it in two sentences. Like, how is this word related to every other word of this sentence? How is this word related to every other word of this sentence? That is actually what cross attention is. We'll discuss it in detail. But for now, this is how attention pattern looks like. Attention pattern is nothing but a sequence length by sequence length matrix. And black is almost zero score, white is a higher score, pure white is like the higher the score, the white block is. So I want you to focus on this first one. Yeah, this is very interesting. If you see in English, European Economic Area, in French it is written in reverse. The area in English is attending to this zone in French. Economic is attending to this, I don't know how to say it in French, but this French economic here, and European is attending to this word. So you can clearly see the model has learned which word corresponds to which other word. Like similar thing happens within a sentence. So just like I showed you here, if you see here, the law will never be perfect, but its application should be just. We know as humans, it's refer to the law. The model has learned that okay, it's will refer to the law. That is what model has learned. This is what we wanted it to learn. Okay, so now we know. Now we know how we try to learn, how we learn the relationships and the attention pattern. Moving on. What is the second part? Second part is how do we refine the embeddings? We have these scores. How do we refine the embeddings? So basically, whatever the scores we have calculated, we'll use them. But first, I want to tell you, give you an intuition of why do I want to even refine the embeddings. I've already given, but I'll tell you again. Look at this beautiful picture from a video by 3 Blue 1 Brown. We start with these initial embeddings, right? Any of these embeddings are some high dimensional vectors, which encodes the meanings of only that word. A fluffy blue creature roamed in the verdant forest. This embedding will only capture fluffy but blue and creature. But if I want you, if I say that please imagine a fluffy blue creature, you won't imagine fluffy separately, blue separately, and creature separately. You will imagine a fluffy blue creature like this, right? This is much more. This makes much more sense. So somehow the embedding of this creature should carry the entire meaning. That is what we are doing. Like we are trying to make the information flow from here to this embedding. That is all about it. We are trying to refine the embeddings. So we are allowing the tokens to talk to each other. Like they are like messaging really. So every token is looking at other tokens and seeing like this is what I want. What do you have? What do you have? What do you have? And then they figure out the relationship. And then we calculate the attention score. Then the information flows to me. And now I have a refined embedding. All the tokens are doing this parallelly. So every token is updating, let's say, their own embeddings so that we have better embeddings. That is the idea of flow. So now we have okay, let's look at this formula also. We'll come to it later. Cool. How do we do that is simple. Once we have this scores, we'll just convert the scores into probabilities by softmax. Yeah, the higher the score, stronger is the relationship. So we take this. This is just a mathematical thing. We divided by 8 to introduce numerical stability. Just leave it for now. Softmax say we'll convert these scores into probabilities, and then we'll use these probabilities as weights. Okay, now enters V. V is what we'll communicate. So we have, for every token we have a V, right? Let's say there are 50 tokens, so there are 50 V's, and we have let's say I'm trying to create a new embedding for this word thinking, right? Thinking, we have calculated the relationship by scores. Now we'll take the weighted average of all the V's of all the tokens in the sequence. What are the weights, these relationships, and then we'll add them. Once we add them, this weighted average, of course, we'll add them. The weighted average is the new embedding of thinking. That is all attention is. This is what Z1 is. Simple. Okay. So this is what we want to capture. Now we have covered what attention is. This is what this formula says for attention given q, k, and v. You take softmax of q into k transpose, q into k transpose. This is attention score, numerical stability divided. Take a softmax, convert it into probability, and then multiply it by v. All that which I said is summarized in this line. Okay, we have refined the embeddings. I think this should give you a good enough idea. Now I want to revisit cross attention. So when I said here, what is cross attention is, let's go to this paper. This layer is cross attention. So if you see, two arrows are coming from encoder and one arrow is coming from the previous decoder. So this cross attention, this is, let's say I'm trying to translate I am Shubham in English to मैं Shubham हूँ in Hindi. I from English should attend to मैं, the word मैं in Hindi. This is what cross attention learns. But the funda is simple, exactly same as what we are doing. It's just only that if I'm trying to transfer from one language to another, query will be from, I'm translating from English to Hindi, right? So query will be from I, right? Key and value vector will be from the encoder. Yep. That is how the transformer works. So K and V will be from encoder, query will from the decoder. So I'm translating this word, like I am Shubham from मैं Shubham हूँ. Right, so this word I'll try to search. Okay, this is the word मैं in Hindi, what it relates to in English. So K and V will be from encoder and Q will be from decoder, and then we'll do the similar process. We'll already have these three vectors in our matrix. We'll do the same process. That is how cross attention works. Read this blog. I have like put in efforts to explain everything. You'll understand. Other concept is what is masking. I'll skip masking for now because the video is already too long. But it's a very simple concept. Just read it from this. The other important thing is multi-head attention. I cannot skip this. Whatever I told you till now, whatever is happening in one layer, if you see this one layer, K, Q, and V values, all these are calculated in one layer. We do this parallelly in 8 separate layers. Every layer has its own set of these vectors, W, K, and WQ. WQ, WK, and every layer has different queries. Every layer is doing its own stuff, right? And then we combine the results. Why do we have different layers? Because they are trying to capture different relationships amongst the words. So we do it parallelly. We concatenate the result, and then scale it to whatever we want. So that is all goes behind the scene in the attention layer. In paper, if you see in paper, I'll just show you in paper also really quickly. This is how they concatenate. This is how they concatenate the results, and so that we have the final results. Okay, I think this is enough. In next video, let's try to implement attention. We'll look into the code, how the code is working, and see you in the next video.